So our next set of challenge problems, or problems that we had to work on outside of class, actually had to do with buffer preparation. And so a couple of things to think about here, and I'm going to flip to sort of a blank section here on the last problem, just to have some space to kind of highlight some things to think about with buffers. When we're thinking about buffers, anytime you're going to prepare a buffer, you are always going to need to use two equations. You're going to want to use the Henderson-Hasselbalch equation, and you're going to want to use the fact that a buffer is made up of a weak acid and its conjugate base, and the overall concentration of the buffer in terms of the millimolar or molar concentration of the buffer is really a combined concentration of both of the weak acid and its conjugate base. So again, having two equations is important because remember, if we're just using the Henderson-Hasselbalch equation, when we solve for the ratio of A minus to HA, this tells us the relative amounts of each that we need to have, such that we're going to shift the pH from the pKa value if they are not present in equal amounts. So again, that is a relative number. We can't go into the lab and measure relative numbers. So by having an equation that allows us to, a second equation that allows us to solve for a unique unknown, we can get to concentrations of A minus and concentration of HA, which are specific absolute numbers. And again, this is something we'll talk about a lot in lab, is the difference between relative amounts, which have to do with a certain ratio between species, and we may not necessarily know what the actual amounts are, and then absolute values, absolute numbers, absolute quantities, where we actually do know what these are. So having both A minus and HA as unknowns, again, we can use the Henderson-Hasselbalch equation to calculate relative amounts, but to calculate absolute amounts and find what these are specifically, we'd need to have a second equation that we could use to solve for that. And so just a couple of highlights here with how we're going to want to think about both of these problems. The first problem that we're going to go through basically is where we have A minus as a solid. And by having A minus as a solid, we can use the molecular weight to figure out the amount that we're going to weigh. We're going to have HA as a liquid. And then by using the concentration, generally in molarity, we're going to be able to figure out the amount that we can measure in terms of a volume and ultimately dilute. So that first problem is going to be pretty straightforward. But again, I hope to highlight for you guys when we go through both of these problems that they're set up at the outset the same, where we have to first use two equations to be able to solve for the absolute amounts of A minus and HA that we want. Just a little bit of a preview with the second problem. Basically, we're going to have the concentration of HA that's going to represent all of our buffer component. And then what we're going to do is we're going to add a strong base, and we're going to make the amount of A minus that we need in the solution. And we're going to use solution stoichiometry to be able to figure out exactly how much KOH we're going to add. So hopefully that overview made sense. We're going to go through now and work through both of these different buffer problems. So the first thing to kind of highlight with this problem, and it's something that I'm going to get rid of in future discussions, this N is supposed to be an N. It stands for normality, which is a way of kind of accounting for the fact that some acids might not be monoprotic. Acetic acid is a monoprotic acid, so normality and molarity are the same. But I can honestly say I've never seen normality in any of the acids that I've had to think about using in biochemistry. So we're just going to cross that off, and we're going to say that that is glacial acetic acid, which has a concentration of 17.6 molar. Okay, so working through this problem now and highlighting the fact that, again, we need to use two equations, two unknowns. We'll start with the Henderson-Hasselbalch equation. So pH equals pKa plus the log of our A minus over our HA. Again, our second equation is the fact that A minus plus HA is going to equal the total solute concentration. So putting in specifically what these values are, we want a pH of 3.9. The pKa for acetic acid we're going to use as 4.76. In this case, sodium acetate is going to be our conjugate base, and our weak acid is acetic acid. Kind of just jumping over here for a second, again, the concentration of sodium acetate plus the concentration of acetic acid is going to equal 200 millimolar here. We're making a 0.2 molar acetate buffer, which is 200 millimolar. So going through and kind of solving for our ratio here, we're going to have negative 0.86 equals the log of our sodium acetate over acetic acid. Again, 10 to the negative 0.86 is how we're going to get rid of this. So 10 to the 0.1380 is the ratio between sodium acetate and HOAC. Just as a quick check here, so again, this number is less than 1, which means these are not equal. A smaller number, less than 1, again, is going to tell us that we are a little bit heavy in terms of our acid, and that is consistent with us wanting to have a pH that's less than our pKa. So just kind of a good reminder, refresher there in case you have a situation where you're worried that you might have put something in the wrong spot. That's a good kind of check that we have there. What we're going to be able to do now is I'm going to solve this equation for sodium acetate concentration. So 0.1380 times HOAC equals my concentration of NaOAC. And then I'm going to be able to take this and I'm going to substitute this in over here. So now I'm going to have 0.1380 times HOAC plus HOAC equals 200 millimolar. So again, you can think of this as being 0.1380x plus 1x. So this ends up being 1.1380 times HOAC equals 200 millimolar. Solving this for x tells me that my HOAC concentration is going to be 175.75 millimolar. Don't worry right now about significant digits and so forth. We want to make sure that we're sort of keeping things until the very end. I can substitute this back into either equation. I personally find that it's easiest to substitute it back into this equation. So again, 200 minus 175.75 is going to give me my sodium acetate concentration. So that's pretty straightforward. So my sodium acetate concentration is going to be equal to 200 millimolar minus my 175.75 millimolar, which is again that guy. And that equals 24.25 millimolar. Now that I've solved this, remember in our problem when we kind of had our overview here, we said that we were going to have one thing that was a solid. So our solid is going to be our sodium acetate. We want that concentration to be 24.25. millimolar. So 24.25 millimole per liter. We're going to be making 100 milliliters, so 0.1 liters. Molecular weight, 1 millimole is 82.03 milligrams. That ends up being 198.92 milligrams of our sodium acetate. And then for our liquid, which we are going to be diluting, we're going to have acetic acid. That concentration again is going to be 175.75 millimolar. I can simply use an M1V1 equation. 17.6 molar times, we need to figure out the amount that we're going to take to equal, and I'm going to put this now into molar because that was what my stock concentration was. I'll keep this guy as milliliters so that my volume will end up being milliliters, and I end up with 1.00 milliliters. So again, the final relevant pieces of information here in terms of the pieces that we need to take and the pieces that we need to put then into our Mad Libs, the fact that we're going to have and weigh out 198.92 milligrams of sodium acetate. We're going to add that with 1.00 milliliters of glacial acetic acid. We are going to put this into a 100 milliliter volumetric flask. And again, we can dilute, if we're going to assume that the pH is going to be 3.9, we can dilute it to 100 milliliters in that volumetric flask. If we wanted to double check the pH or even needed to adjust the pH, we would mix these together first in, say, a 100 milliliter beaker with, about 100 or 80 milliliters of water. Adjust the pH as necessary, and then finish our final dilution to 100 milliliters in that volumetric flask. So I went through that fairly quickly, not a lot of words there, but hopefully that sort of makes sense. I'm going to flip now over to our second problem here. And again, just to highlight and review with this second problem, remember what we're going to have is we're going to have essentially only one component that we make our buffer from. We're going to use our acetic acid. So all of our acetate is going to come from acetic acid. Normally, right, in a buffer, we'd have acetate in two flavors. We'd have it as a weak acid and its conjugate base. We're starting now by having all of the acetate as the weak acid. We're going to be adding in KOH at a fixed amount once we figure out what the ratio is, so that we can take a portion of this HA and convert it to A- in solution so that we get the ratio that we want. So just like we've talked about before, we do want to make sure that we use the same two equations, do the same calculations to be able to figure out the ratio that we need, and then ultimately the absolute amounts that we need of both our weak acid and our conjugate base. So let's go ahead and start with that. So again, pH equals pKa plus the log of A- over HA. And then our second equation is A- plus HA is going to equal 300 millimolar. pH that we want this solution to be at is 4.47. pKa is 4.76. In this case, our A- is going to be our acetate, and our HOAC is going to be our weak acid. Go through just like we did in our last problem, solving for our ratio. Negative 0.29 is going to be equal to the log of OAC minus over HOAC. 10 to the both sides will allow us to simplify this, and we get the ratio is 0.513. It's the concentration of acetate over acetic acid. So again, solving this for one species, HA times 0.513. It's going to be equal to, let me put this in what we had here. We had put that in as HOAC. Is equal to OAC. And I'm going to take and substitute this in up top here. So again, I'm going to have HOAC times 0.513 plus HOAC equals 300 millimolar. Again, remembering that this is really like 0.513x plus 1x. So I'm going to get 1.513 times my acetic acid concentration equals 300 millimolar. So my acetic acid concentration is going to be equal to 198.3 millimolar, and then my A minus concentration is equal to 101.7 millimolar. So again, just to highlight, the Henderson-Hasselbalch equation gives us a ratio of our weak acid to our conjugate base that will give us the pH that we're interested in. Again, this ratio being less than 1 means that we are acid heavy, so our pH is going to be less than our pKa. We need to, however, have the second equation that normalizes those ratios to a fixed amount so that we can get the actual absolute numbers that will give us this ratio. So now is where this problem becomes a little bit more challenging, because what we need to realize, and we're going to just kind of draw a little picture here to sort of think about what happens. The 300 millimolar really all comes from our HOAC concentration, our acetic acid concentration. So we can begin this problem with sort of a simple M1V1 equals M2V2 to figure out the concentration of HOAC that we want. So M1V1 equals M2V2. So we're going to have a 2 molar acetic acid solution. We need to figure out the amount that we're going to take such that we dilute it to get a 300 millimolar, 0.3 molar solution, and we want 5 liters. Pretty straightforward calculation tells us that we need to have 750 milliliters of our acetic acid. So just to kind of give a little picture here, we're going to take this 750 milliliters of our acetic acid. So this 750 milliliters really means that our acetic acid concentration is 300 millimolar. What we're going to do in the rest of this calculation here is realize that we're going to be adding KOH, and we're going to take some of this acetic acid as 300 millimolar, and we're going to make it into acetate, right? So we're going to have KOH plus HOAC is going to generate H2O and OAC minus. So what we can think about here is the fact that we know right now this concentration is 300 millimolar, and we have 0 before this chemistry happens. But what we know needs to happen is we need to make this guy increase to 101.7, and this guy is going to decrease by 101.7. And at the end of the day, this means that we are going to be adding so that our KOH would get to a concentration of 101.7 millimolar. So hopefully, let me run through this little calculation and this will make sense. We know that we want our final concentration of acetate to be 101.7 millimolar. If we're going to have 5 liters of that solution, that's going to scale up the amount of acetate that we need to generate in terms of total number of moles. And our chemical equation that we have here shows us that we're going to have 1 millimole of acetate reacting with 1 millimole of KOH. Now, at the end of the day, we know that we have a solution of KOH that's 2.5 molar, so that's 2,500 millimole of KOH. in 1 liter. And so this tells us that we're going to need 203.4 milliliters of KOH. And why this is important is part of this problem is having us think about how we could, realistically make this solution. And if you went and made this solution and didn't leave yourself, the volume that you'd need to have, this 200 milliliters of KOH, you might end up wasting a lot of material because you'd be greater than the 5 liter of total solution. In addition, it's going to help save us time at the pH meter because we still are going to probably want to check the pH of this. And if we didn't know how much KOH we were going to add, it's kind of like those burette experiments that you had in Gen Chem. The first time you do a titration with a burette, you have to go pretty slowly because you have no idea how much you're going to need to add. After you've done the first one, and you're going to repeat that experiment just to see how precise kind of your titration skills are, then you might be able to go a bit more quickly, get through maybe 80% of the titration before you know you're getting close. That's sort of the equivalent here. If we didn't know that we needed to add 200 milliliters of KOH, we might be sitting there dropping it in like dropwise until we got to the pH that we'd need. Because remember, the purpose of doing a buffer this way is we're not grabbing two things off the shelf. We're just making a buffer from one component, and then we're using a strong base to generate the other buffer component in solution. And so we're going to need to be at a pH meter in order to tell when we're at our equivalence point. Truthfully, for any buffer preparation, even for this one, you probably are going to want to be checking the pH because you never know if the concentrations of your solutions are spot on, or even if the water that you're using to dilute is a perfect pH 7.0, which can have a significant effect as you're diluting things. So hopefully this problem made sense in terms of thinking about two different ways to make a buffer. One of them is a little bit more involved in terms of the calculation, but a little bit more simple in terms of only needing one component, this second one that we did. The first one is a little bit more of a traditional way of thinking about making a buffer, probably going to spend less time at the pH meter. But again, you need to have both of those components in your laboratory in order to be able to do them. And at the end of the day, you're probably still going to want to be checking your pH with a pH meter.